Let's talk about the situation where in an experiment, every outcome has the same likelihood of occurring. Every outcome is equally likely. Let me give you a couple of examples just to make sure we know what we're talking about. So the first one, and kind of the simplest you can imagine, is flipping a coin. There are two outcomes, heads, tails, and for all intents and purposes, the chance that you get heads is 50%, the chances that you get tails is 50%. Or maybe something along the lines of drawing a card from a deck. There are 52 cards. They're the 52 outcomes. And each card, as long as it's shuffled and you're just picking one at random, is equally likely to be picked. Or another one is, of course, rolling a die. Each number is equally likely to occur when you roll a die. A 1, a 2, a 3, a 4, a 5, or a 6. And what's nice with equally likely outcomes is you can mathematically determine the probability of events now. Remember, events are made up of outcomes. So the probability of some event occurring is the number of successes that are in your event over the number of total outcomes. So a very simple one is, let's say our event E is just the, let's say, the Jack of clubs. That's the only thing in our event E. It's just the single outcome of the Jack of clubs. Then the probability of E occurring, well, there's only one Jack of clubs in a deck of cards if our experiment is just drawing one card randomly from a deck. And how many cards are there in total? There are 52. So the probability of drawing the Jack of spades in one random draw is 1 out of 52, which is roughly, if you like, 1.9%. You can convert that the usual way you convert fractions to percentages. Okay, let's look at one that's slightly more complicated, and it's related to an example that we did before. So it is the event E being drawing a heart or a face card in one draw. Our experiment, let me just write this so we're sure. Experiment is drawing one card randomly from a deck. So that's our experiment. Okay. So what is the probability that we draw a heart or a face card? So if you remember from previous videos, there are 13 hearts in a deck. There are 12 face cards. 13 plus 12 is 25. But remember, 3 of those face cards are also hearts. So we need to subtract the Jack of hearts, the Queen of hearts, and the King of hearts. We need to subtract 3 from that total because we don't want to count the Jack, King, and Queen of hearts twice. So in total, there are 22 hearts or face cards in the deck, and it's over a total of 52 cards in the deck. And again, I can give you a rough percentage. That is around 42.3%. 3% rounded to the nearest tenth of a percent. So that, in essence, is how probabilities of equally likely outcomes are counted. Let's have a look at a few more examples. Let me scroll down here. So our experiment here, let me be kind of explicit. Our experiment is rolling a die, a regular old 6-sided die, and recording the outcome. So let's say we have the event F. What we're interested in is when the number on the die is even. And of course, there are 3 even numbers, 2, 4, and 6. So our event F, I just picked the letter F because we already used E. It doesn't really matter. You can name events whatever you like. So it is, in fact, these 3 outcomes: the outcome 2, the outcome 4, the outcome 6. So you can imagine we could have a little Venn diagram here. Here's event F. Inside is going to be 2, 4, and 6. And outside in our sample space are the other ones, 1, 3, and 5. So they're all the possible outcomes. That's our sample space, 1, 2, 3, 4, 5, and 6. And the event F are the even numbers, 2, 4, and 6. And the probability of F occurring is, of course, well, there are 3 even numbers over 6 possible outcomes, which is, we can simplify to 1/2, which is, of course, if you like, if you wanted to convert to a percent, you don't need to every time, but if you wanted to, that's 50%. Let's look at this example. So this experiment is going to be, let's say experiment, sorry. We'll write it like this. And it's going to be, rather than rolling 1 die, we're going to roll 2 dice and sum the outcomes. Okay. So we have, first of all, we have this event G we care about when the sum of the 2 dice is 8. Now you could think, well, maybe these aren't equally likely outcomes, because getting a sum of 2 on 2 dice, that happens exactly one way, just getting a 1 and a 1. But getting a sum of 7, happens in loads of ways. 1, 6, 2, 5, 3, 4, 4, 3, whatever. So we can't think of just the sum as our outcomes. It has to be the unique dice roll. So we have to be a little careful about this. So we want to know, how big is this set G? How many outcomes are in this set? Well, let's list all possible outcomes first. I'll do it in a little table since we have 2 dice. So this will be my first dice. We'll go down vertically, and the second die will go horizontally. I should have said the first die for the first one, of course. And our possible values on our first die, we can roll a 1, we can roll a 2, we can roll a 3, a 4, a 5, or a 6. And on the second die, it's the same thing. 1, 2, 3, 4, 5, and 6. Okay. Well, in this chart, what I'm going to have is the sum of the 2 dice. So in row 1, column 1, 1 plus 1 is, well, let me use the pen here, sorry, 2 Then if we roll a 1 on the first die and a 2 on the second die, 1 plus 2 is 3. Similarly, 4, 5, 6, and a 1 on the first die, 2 on the second, or 6 on the second die is 7. And we can fill the chart in the exact same way for the other rows. 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, and 12. So, here are all of the possible outcomes. A 1 and a 1, 1 on the first die, 1 on the second die, and we're going to count that as a 2. So, how big is this event G? How many outcomes? Well, let's see all of the outcomes that have a sum of 8. Well, here they are here. 1, 2, 3, 4, 5. There are 5 of them. So n of G, the number of elements in G, and just as a reminder, this notation here means the number of elements or outcomes in the set or event G is 5. And they are rolling a 2 on the first die, a 6 on the second die, so 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. So there's 5 different outcomes. So the probability of G occurring, well, there are 5 ways of getting success, 5 ways of getting a sum of 8. Here they are in this table. And how many different total outcomes are there? Well, there are 6 choices for your first die and 6 choices for your second die. They're independent rolls. Of course, whatever you roll on the first die doesn't affect what you'll roll on the second die. So 6 times 6 is 36. There are 36 total outcomes in rolling 2 dice. So our probability is 5 out of 36, which is roughly 13.9%. But it's fine to leave it as 5 over 36 if you like. A few rules about probability. And I want to note that these hold for all experiments. It doesn't have to be just for equally likely outcomes. So this holds for absolutely all experiments. The first one, and this is kind of obvious, but the probability that any event occurs has to be between 0 and 1 inclusive. Of course, remember 0 means that the event will never happen. 1 means that the event always happens, and any number in between gives a measure of the likelihood of that event occurring. Secondly, this is important too. Let's say you do have an experiment. Again, it doesn't have to be equally likely outcomes. Let's just say all outcomes. And let's say there's n of them. So let's call them x1, x2, x3, x4, all the way up to xn. Well, if you add up the probability of all of these outcomes occurring, you have to get 1. Something must happen. Remember, outcomes are simple events. There's no way for 2 outcomes to have anything in common. So all of these guys are mutually exclusive. Outcomes are mutually exclusive. So either outcome 1, x1 happens, or outcome 2, x2 happens, or x3 happens, or x4 happens, all the way to, or xn happens. That's all of them. If there were any more, we'd list them. So the probability It's or, so we add them together. All of these guys are mutually exclusive, so we don't have to worry about any sort of double counting or anything. So if we sum the probabilities of the outcomes, we get 1. Something must happen. Either x1 happens or x2 happens, etc. So the probability, if we add up all of these, is 1. Let's do a quick example over to the side here to make sure we get this. Let's say that, for whatever reason, let's go back to bits and bytes. So let's say I have a bag of bits and bytes, and let's do it like this. In the top, I'll list the bit and bytes. So we have the Shreddy, the Cheerio, the pretzel, and the cheesy bit. And underneath, I'll have the probability that if I reach my hand in that bag of bits and bytes, that I pick out that particular bit and byte. So let's say this one is 0.4, the Cheerio is 0.3, the pretzel, let's say, is 0.2. What is the probability of picking out a cheesy bit? Well, we know that the probability, these are all 4 outcomes, by the way. There are no other bit and or byte we can pick out of the bag. There are only 4 different types, and we know the probability of 3 of them. So we know that the probability of picking a Shreddy plus the probability of picking a Cheerio plus the probability of picking a pretzel plus the probability of picking a cheesy bit has to equal 1, since they are all of the outcomes. And, well, we know these, at least 3 of them. So this is 0.4 plus 0.3 plus 0.2. And we don't know the probability of picking our cheesy bit, but we know that equals 1. And I'll leave it as a small little exercise for you guys. You can check that the probability of picking a cheesy bit is, of course, 10%, 0.1. So that's the idea of outcomes having their probability sum to 1. One more idea I want to talk to you about right now is the idea of complementary events. And it's kind of the same idea as the complement of a set. So it's everything not in that set. The complementary event is everything not in that event. So if we were talking about dice, and I had an event E that was, let's say, 1 and 3. So again, just rolling a 6-sided die, and event E is rolling a 1 or rolling a 3. Then the complement, and we write it like this, just like set notation, is everything else in our sample space, in our universe, that isn't in our event. So a 2, a 4, a 5, and a 6. So that's the idea of complementary events. Let's look at a quick example here. Let me scroll down. So let's say the experiment is choosing a natural number from 1 to 10 inclusive, so the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 randomly. So I want the event E to be square numbers. So they're numbers that when you multiply another number by itself, you get that number. So 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. That's too big, since we're only dealing with the numbers from 1 to 10. So the square numbers are 1, which is 1 squared, 4, which is 2 squared, and 9, which is 3 squared. So, and we can draw a little Venn diagram here, just so we see what's going on. So, here is E. I'll do it in red. We have the numbers 1, 4, and 9 in here. But the other numbers in our sample space are the numbers from 1 to 10 that aren't 1, 4, and 9. So they will be outside. So it'll be a 2, a 3, a 4 is inside, so a 5, a 6, a 7, an 8, 9 is inside, and a 10. So the complement of E is all of those. 2, 3, 5, 6, 7, 8, and 10. And of course, if you think about it, the idea that the probability of each outcome added together is 1 leads to this idea here. For any event E, the probability of that event happening plus the probability of its complement happening has to be 1. And you can rearrange that if you like. Probability of a complement is 1 minus the probability of the event itself. And of course, what is this saying? Remember, a quick note here, that E, event E, and its complement is definitely mutually exclusive. So their intersection has nothing in it. There's no element that happens and doesn't happen, of course. So the definition of a complement is it's outside of an event, so there's no way for an element to be both in E and outside of E at the same time. So E and its complement are, of course, mutually exclusive. And if you think about it, the probability of an event happening plus the probability of the event not happening has to be 1. Because they're really the only two possibilities. Either E happens or E doesn't happen. That's it. So those probabilities together have to add up to 1. And a quick example, of course. Well, let's say that you're interested in the probability. In fact, maybe I'll talk about an event first. So let's call the event F, I guess. So this is going to be the event in drawing a card from a deck of 52 cards, of drawing a non-heart number card. So, and I'm going to count ace as a number. That's the number 1 I'm thinking of. So you could try and solve this problem directly and think, well, how many cards are not heart number cards? But if you realize, this is kind of the key. So note that F is actually the complement of event E from way back in a few examples ago, where E is the set of hearts or face cards. If you're not a heart or face card, it must mean you're a non-heart, non-face card, a non-heart number card. And we already worked out this probability. We worked out that that was 22 over 52. So we know that the probability of F is going to be 1 minus the probability of E. So this is 1 minus 22 over 52, which is, you can change 1 to 52 over 52 if you like, and subtract, and you get 30 over 52. So the probability of drawing a non-heart number card is 30 over 52.